Today we will learn about histogram of varying width. In the previous video, we learned about the histogram of uniform width, in which we represent the number of words the students typed in 5 minutes as histogram of same width. Suppose a student classified these data in this way. Is the table the same as the one made in the previous video? No. Here we see that the class width of first class interval is 100 minus 60 is equal to 40. The class width of the second class interval is 120 minus 100 is equal to 20. And the class width of the third class interval is 180 minus 120 is equal to 60. Thus, the class width of the class intervals are different in this frequency distribution table. In order to represent these figures, the student drew the histogram in such a way that the length of rectangles to be drawn for class intervals was proportional to frequency. Did he draw the correct histogram? Think. No, this is an incorrect histogram. Let's understand the reason for this. We know that the area of a rectangle in a histogram is proportional to the frequency it represents. According to this statement, the area of each rectangle here should be proportional to the frequency. Since the frequencies of the class interval 100 to 120 and the class interval 120 to 180 are the same, the area of rectangles representing them should also be same, but the area of both appears different here. We can also understand it mathematically. Here we see that the rectangle representing the frequency 15 of the class interval 100 to 120 is 1.5 units in length and 1 unit of width. Thus, the area of this rectangle is length multiplied by width is equal to 1.5 square units. Similarly, the rectangle denoting the frequency 15 of the class interval 120 to 180 is 1.5 units in length and 3 units of width. Thus, the area of this rectangle is equal to 4.5 square unit. The ratio of the area of these rectangles is 1 by 3, but the ratio of frequency of both these class intervals is 1 by 1. Since the ratio of areas of rectangle is not proportional to their corresponding frequencies, the areas of rectangles are not proportional to the frequencies here. That is, these histograms show the wrong frequency of the corresponding class intervals. So this histogram is wrong. In the histogram, the area of rectangles must be proportional to frequency. The width of the rectangles depends on the class width of the class. The class widths here are different. Therefore, the width of the rectangles will also vary. If we want the area of rectangles to be proportional to the frequency, we must change the width or length of the rectangles. But the class width of each class interval is fixed. So, we cannot change the width of rectangles. So, we have to change the length of rectangles. Can you tell us how we will make this change? Think. Let us tell. For this, we will find the lowest class width of class intervals. Here, the class intervals are 100 to 120, class width 20, is the minimum class width. Now, we will multiply the result by the minimum class width by dividing the frequency of that class interval by the width of that class interval to find the length of rectangle of each class interval. For example, here the length of rectangle of interval 60 to 100 can be obtained as follows. Similarly, the lengths of the rectangle of other class intervals can be obtained in this way. Now, we will draw rectangles with a suitable scale for each class interval. Here, we have taken 1 unit is equal to 20 words on the x-axis and 1 unit is equal to 5 student scale on y-axis, from which we have obtained the histogram in this way. Now, you stop the video and find out whether the area of rectangle in this histogram is proportional to the frequencies or not. Try it. You must know that now the area of rectangles is proportional to frequencies. Hopefully, you can now draw a histogram of varying width for a graded frequency distribution that has different widths of class interval. Today we have learned histograms of varying width. In the next video, we will see some examples of histogram.